This afternoon, we're going to start off with, we've got 6 talks. We're going to hear sort of an architectural overview of 6 different ZK VMs. We're going to start off with OpenVM. They're going to be, Yi's going to speak about real-time proving for Ethereum L1, the modular approach. Yi, thanks for being here.
Hey everyone, my name is Yi. I'm one of the co-founders of Axiom, and yeah, I would love to tell you about how we achieved real-time proving for Ethereum using OpenVM. Maybe if the slides will work, I can tell you more. Okay. Oh, click the, OK, great. Cool. So first of all, OpenVM we call a ZK VM framework because it is meant to be customizable and extensible. What that means is that although we support certain ISAs, we don't like to bake that into the framework, and we want to allow developers the choice to modularly build the ISA that they need for their purposes while still using the same framework. So currently, we offer a Rust front end and also use what we call a no CPU architecture to enable all of this. Now, to talk more about the modularity at the ISA level, with OpenVM, we allow developers to build an ISA through what we call VM extensions. These are groups of opcodes that interoperate over common memory spaces, and developers can add or modify extensions while importing the core OpenVM as a library. So for example, we have RISC-V support through an extension, and core OpenVM does not know about any particular ISA. So out of the box, OpenVM can prove Rust programs, but developers can also customize by creating their own VM extensions for workloads of their choice. We believe there are some workloads, like machine learning inference or particular signature schemes, that will require this approach. So now let's talk about what everyone is here for, which is how to apply OpenVM to Ethereum. So first of all, we launched at the beginning of the year, and at that point, OpenVM was frankly not very efficient. We've been able to make about a 3x improvement every 3 months since then, and on a benchmark block, block 21 million, we now have sub-cent proving and also real-time proving. So overall, we've been able to achieve over 30x performance improvement on both cost and latency. And so as everyone saw in the demo, we're now able to prove Ethereum in real time on 32 GPUs. So in this histogram, you can see that our P50 latency is around 7.7 seconds, and we have a P99 latency of a little over 10 seconds. This is on a range of 1,000 recent L1 blocks from, I believe, yesterday. So in this talk, I wanted to talk through 3 areas of our architecture, which I thought were particularly relevant to real-time proving. So that's our no CPU architecture, which is the way we construct OpenVM to allow a modular architecture, the optimizations we made to execution through ahead-of-time compilation, and finally, our overall distributed proving pipeline. So our perspective with OpenVM was that existing ZK VM designs really kind of overfit to physical processors. When you design a CPU, of course, there's a physical chip, and it's very hard to make it configurable, and you must specialize to a specific ISA. A lot of ZK VM designs kind of emulate this by having a central CPU circuit that knows about every opcode and coordinates all of the VM activity. So with OpenVM, we've introduced what we call a no CPU architecture, where we do just that. We remove the CPU. And in ZK, we're actually able to constrain execution consistency without doing it in a single chip. We're somehow distributing it through a consistency check with randomness. This has 2 benefits. The first is that we're able to just reduce the trace size by removing this large CPU circuit. And the second is that we're able to plug in new opcodes into the system without imposing changes to other circuits. And so this makes modularizing the ISA much more straightforward from a development perspective. OK, so in our distributed proving pipeline, we have roughly 3 steps. The first is that we actually have to execute the guessed program of interest, the Ethereum state transition function, on the CPU. So that's done in serial. After that, we execute again in pre-flight execution to prepare for trace generation. And then finally, we do GPU proving. So as you can see, the only serial step in this process is the CPU execution. And as a result, for something latency sensitive like real-time proving, it's a pretty critical bottleneck. Now, the core challenge when proving an ISA that is not the exact same as the one running on your CPU is that you essentially need to interpret the ISA. And we went through several phases where we discovered that interpreters are pretty slow. If you implement a naive interpreter, maybe with handwritten Rust, you'll probably achieve something like 20 to 50 megahertz. If you go a little bit deeper and add things like tail calls, you'll get to something like a couple hundred megahertz. So we did this previously, and we had RISC-V execution at about 380 megahertz. And in our push for real-time proving, we implemented ahead-of-time compilation of the state transition function, namely transpiling every RISC-V opcode to x86 opcodes and storing as much as possible in the lower number of registers. Now, one particular difficulty in doing this in our modular design is that we needed to handle extensions that we did not want to translate to x86 assembly. For example, things like the catch-ack hash or elliptic curve precompiles. And for this, we had to support mixing and matching handwritten x86 assembly for RISC-V and just native Rust that's already optimized for these special operations. So to give a sense of the scale of the results, I said before that with our best interpreter, we're about in the 300 megahertz on execution. With ahead-of-time execution, we're able to achieve over 2 gigahertz, which is roughly half of native execution. We think this is pretty close to best possible, since for every RISC-V cycle, we're using approximately 2 x86 cycles. And as you can see, on a relatively tail case block in the 23 millions with 43 million gas, this decreases the execution by about a 3x. You may ask why it's not a 8x, and the answer is that there's already a significant amount of the execution of the block that is not in emulating RISC-V, but rather in emulating precompiles. So this was a big step in reducing the latency of the only serial component in distributed proving. So after distributed proving, or after execution, the proving process for OpenVM is fully parallel. So we do trace gen fully on the GPU, and then we do proof generation also fully on the GPU to remove any sort of host-to-device memory transfer. All right, so what's next? As everyone has seen in the demo, real-time proving for Ethereum is now a reality. And for ZK VMs in general, we feel like we've reached a point as an industry where performance is on a path to being not an issue for applications. And what we think will be important is actually flexibility and customization for different applications. So to that end, on the OpenVM side, we plan to add different ISAs and front ends. For example, support for things like RV64 or WebAssembly, as well as the ability to synthesize precompiles in a more automated fashion rather than writing them always by hand. Moreover, we now want to cache in our modular design and have the ability to apply OpenVM to more domain-specific computations with extensions that are very outside of a typical ZKVM compute pattern. So look for more from us about that in the next couple months. So if you want to learn more about OpenVM, you can check out our docs site or our GitHub. And if you're interested in working with the Axiom team to implement OpenVM for your application, you can check out our link on the slide. So thanks for listening, and happy to take any questions.
Thanks so much, Yi. We've got one question here. What is the most exotic and interesting ISA you see people looking to implement in OpenVM's framework?
I feel like the most exotic ones are different ways to implement WebAssembly. And I think the biggest advantages of WebAssembly are that it offers a more virtualized embedded systems backend for different languages. But there are certain aspects of WebAssembly which make it a little bit more difficult to implement it as ZKVM. So people have been trying out different intermediate forms on OpenVM.
Excellent. What does success look like for OpenVM?
Yeah, I would say the broader problem that we wanted to solve with OpenVM is the ability to apply ZK to a range of computations that really matches the type of computations that happen in the broader world. As an example, if you look at a typical application, there's a database, which is currently not really a concept in ZK. And if you want to emulate something like that in ZK, we feel you need a more general architectural framework. So for us, success would be that there's a smooth pathway for developers to combine things which look like ZKVMs with things that currently look like custom circuits.
Amazing. Thank you very much. And yeah, great work.
Thanks, everyone.